course, is very important in quantum information science as we have small quantum processors and we want to be able to link them, as well as quantum sensors. We want to distribute the sensing over space. So Kaushik is interested in addressing research questions and challenges that lie across the different layers of a full quantum networking stack towards realizing the future quantum internet. And so we're very pleased to have you, and I'll let you take it away. Thank you.
Thank you, Vanita. Thank you very much for the kind introduction. And yeah, thank you, Professor Khan, for the invitation. Very, very happy to be here. Great to spend World Quantum Day celebrations here. So yeah, I'm going to talk about quantum networking. So we already heard a little bit about quantum networks in our discussion before, and so I titled my talk "Quantum: The Nuts and Bolts of Quantum Networking." And when you think of nuts and bolts, you would imagine I'm going to talk about the hardware, but I'm rather going to talk more about the protocols that the hardware would use to talk to each other. So I'm slightly, a level of abstraction above the hardware is where I'm going to talk about today. But we will look at the components that would make up the quantum internet. So here is the outline for my talk. Since I am the first speaker in this series of talks today, so I would give a brief introduction to the quantum information technology revolution that is currently underway and all the buzzwords that we are all familiar with, just briefly, and then talk about quantum networks. And in particular, I want to draw your attention to the real challenges in architecting quantum networks. What are the challenges and also opportunities, and what are the problems that distinguish quantum networking from classical networking, and how methods are being currently pursued? What are the methods currently being pursued? And so in that regard, I'm going to focus mainly on the bottommost layers of the network stack. So this is, the physical layer is going to be made up of these components, the hardware, but right above there is how do the physical layers talk to one another. And so that's, I'm calling it quantum data link layer. And so I'm going to talk about quantum repeaters and switches. And we'll show some brief results on this topic from my group and give you a brief outlook for the future. So, so the reason we are celebrating the Quantum World Day today is the World Quantum Day today, or on the 14th of April. We've seen this tremendous interest in quantum information technologies over the last decade or so. This is a resurgence from, there was the first wave of quantum, information in the 90s when Peter Shor came up with the Shor's algorithm. And, we saw that quantum computing can provide, speed ups in solving certain kinds of problems. More recently, we are actually getting to build such devices now that can potentially be scaled up to actually, implement such algorithms. So yeah, quantum computing, so if you look at quantum technologies, there's this new paradigm of that quantum mechanics avails in computing, sensing, and in communications. And all this is broadly, what people refer to as, quantum 2.0. There is this second quantum revolution that we are currently in. And so there is a lot of interest in this area now. Now, I don't need to introduce the platform for quantum information technologies to this crowd, but just for completeness, we are talking about qubits that are the workhorse of quantum information processing. These qubits are essentially, two-dimensional quantum systems that can be initialized in states that are, that can be more general than the kind of states that we're used to in classical computing. So here you can you can have the so-called superposition of states that forms an important, that is one of the important features of quantum information that is one of the things. And there is also quantum entanglement, which is that you can have qubits that share certain correlations that are unparalleled, that don't have a classical counterpart. And so if you have two qubits in an entangled state, they can show maximal correlations that cannot be seen in the classical world. For example, if you have two qubits that are in a maximally entangled state, if you ask them the same set of coordinated questions, you get coordinated answers. And this is independent of the question you ask. So that's something very unique to quantum mechanics. And this is the phenomenon of entanglement. And here I'm showing that you ask different questions, but as long as the questions are coordinated, you see this maximal coordination in the responses that the quantum systems give. And this is the feature of phenomenon of entanglement. And entanglement is believed to be the real powerhouse, the workhorse of all these speedups that we see in quantum algorithms and also in quantum sensing. Yeah, so physically speaking, there are different platforms on which these qubits can be realized. So we can broadly classify them into matter-based platforms and photonic platform and the photonic platform. So among matter-based qubits, you have trapped ion qubits that are, there's a variety of qubits, trapped ion, superconducting circuits, color centers in diamond, nitrogen and silicon vacancy centers. There's, Rydberg atoms. These are neutral atom arrays. Each has its own pros and cons, and we don't have a front runner just yet. There is photonic qubits, again, a variety of ways you can encode. You can basically have these quantum states of light that store quantum information that you can process. Now, I want to, so we mentioned quantum computing, quantum sensing. If you want to think of them together in one framework, I would just call it quantum information processing, where you are, the name of the game is to basically prepare your systems, the quantum systems, in some initial state. And then in quantum computing, the way just as we would imagine, you have a problem of interest. If you can come up with an algorithm to solve that problem that prescribes a circuit for you, and you want to implement that logic circuit on those set of qubits that you're employing towards this task. And so, yeah, you would apply what, your circuit decomposed in terms of, a universal set of gates that are native to the hardware that you're using. And so you would have your initial states of these qubits, which are the workhorse here, being transformed by the logic gates, the logical circuit. And you hope to learn the outcome of the answer to the question when you measure the qubits, right? So this is how we would imagine performing an information, processing information and learning the output. And now you could also embed sensing in this framework. If you had one of these gates being parameterized by some, unknown parameter that you're actually interested in sensing, and if you allow your qubits to interact with that phenomenon that is encoding that, that's causing that, that you're interested in sensing, you're going to learn about that parameter and in turn sense the parameter. So this is the framework. Now, the real challenge with quantum computing and quantum sensing is that these quantum systems are extremely fragile. So the qubit systems, which are your registers where your quantum information is stored, they are inherently fragile. and I mean, they interact with the rest of the world, and you basically lose the information. This is a phenomenon of decoherence. So that's a huge, huge issue to tackle if we want to actually make use of quantum computing. Then there is also the fact that quantum logic gates are inherently also noisy. So, I mean, it's very hard to perform exactly, I mean, the transformations that you actually care about. And likewise, measurements are also noisy. So overall, you have to deal with a lot of noise. So one way that we could imagine tackling noise is by introducing redundancy in your encodings. And so this is the idea of error correction. Just as we do in the classical world, you can have, you can encode quantum information in a bunch of, you can encode logical quantum information using many physical or data qubits and perform, think of at the physical layer, you have a bunch, a large chunk of qubits, but then you have a higher abstraction where you have logical information, which is what actually is getting transformed. And you can use the same framework for now error corrected, fault tolerant, what is called fault tolerant quantum information processing. And you can hope to solve large problems by preserving, you can hope to solve larger problems by being able to preserve quantum information longer this way. And so the name of the game in quantum computing in the long run is to achieve scalable, universal, fault-tolerant quantum computation. And what is really challenging, so we heard about DiVincenzo's criteria when Chris mentioned in the discussion before. One of the key, questions is like, how do you scale up the number of qubits? And so why is that important? As we just said, when you want to build in this redundancy and get error-corrected qubits, for that you need large number of qubits. And not just that, you also want those qubits to be able to talk to each other. So there's the whole question of architecture. How do you make qubits talk to each other when you scale up? One possibility is with quantum network. The largely widely believed to be the best possibility is to use quantum networks. And the idea is that, you build small modular architectures you build small modules of quantum processors and then have a modular architecture that basically bootstraps these modules in large numbers to scale up quantum computing power. So what I have here is a couple of examples. So the figure on the right is from IBM. I would guess Chris might mention about it in his talk. That like in the future, you would imagine having multiple of these IBM chips that are able to talk to each other through quantum buses, let's say, like where you can shuttle quantum information between those chips and be able to, hence be able to tackle larger problems. And the other picture on the left is an architecture that was named Music. This is from the IonQ, the founders of the company IonQ, where these red modules are essentially trapped ion processors, small trapped ion modules that are connected via optical networks. And you see a large multiplexer in the middle, and then you can imagine that these different modules talk to each other via optical networks. And what they enable is to teleport qubits between these modules. And also, so you can teleport qubits, or you can teleport actions operations that you want to do on qubits. This is the phenomenon of, this is the concept of gate teleportation, quantum gate teleportation. And so, you need these small scale quantum networks. So that is my motivation for quantum networks primarily, that in the near term, we need these to scale up. Down the line, we need this to scale up quantum computing. But people have also, studied quantum networks from the other direction, which is like you have these different technologies, quantum sensors. If you want to actually really realize, the power of sensing, it does make a lot of sense to try to connect geographically separated sensors in a truly quantum fashion, where they share qubits, where they can exchange qubits. And it has been, so there have been a lot of theoretical research on how does the precision capabilities of an entangled sensor network, improve. How is it better than just independent sensors? And we know that there is a quadratic scaling in terms of the number of entangled sensors. There is a quadratic enhancement as opposed to separable individual sensors. And there's also, if you can have long distance networks, then there is possibility of quantum computing in the cloud. So as I was mentioning this earlier in the Q&A session, that very likely the first quantum computers, the first large-scale quantum computers, there are already exist small-scale quantum computers. Even the large-scale quantum computers are going to be, very likely in the cloud, and it's very less likely that we're going to carry a quantum laptop with us anytime in the near future. So that being said, you need to be able to securely connect to quantum computers in the cloud and delegate your quantum computation in a truly quantum fashion, where you're not sending instructions classically, but rather directly, sending qubits from your, let's imagine you have a lab quantum computer, a small scale quantum computer in your lab, and then you're able to access IBM's quantum computer in the cloud, but through a quantum network. Then what that means is that you will be able to, teleport quantum information. And, you could start your computation here, take it to the quantum computer in the cloud, do a large scale problem, and then get the result in a quantum fashion back to your lab. So that's really where we want to get to with large distance quantum networks. There's also other applications like, where if you have a quantum network, you can actually enhance classical data communications. Like there is a recent idea of a quantum data center, where this is actually classical communications, but if you had access to a quantum network, you can retrieve data from a from a data center at higher rates. You can do there is also, other kinds of, quantum enhanced classical data communications. If you had entanglement distributed between a sender and a receiver, you can communicate at higher rates. There is also, I'm kind of giving you these points like in a reverse chronological fashion manner. If you look at quantum networking from in a chronological fashion, like people initially came about it from the idea of quantum key distribution towards secure classical unconditional information theoretically secure classical communications that can be enabled if you had quantum entanglement and so on. So that's the traditional motivation for quantum networks, but I am visiting it from the inside out, because we are interested in quantum computing more today. And so the goal is, my goal is actually towards, across distance scales, where you can imagine small scale, short range quantum networks that basically help you scale up quantum computing power at, single geographical nodes, and also have a quantum network that can connect, different quantum computers, and for that matter, also quantum sensors. How do you actually retrieve data from quantum sensors, process it using a quantum computer, let's say? This is like, what would be like the holy grail of, quantum networking. This is what I would imagine calling a quantum internet, where you have different quantum hardware, most generally also, hardware, I should mention, hybrid distributed quantum information processing, where you have different applications but all, connected, all quantum and all connected in a quantum fashion. That's the natural sort of end game of, having a quantum infrastructure. So I just want to put this out there. We, of course, are nowhere close to, achieving such a thing. But there are steps being taken at all the different components here. So what I do show here is, next up, is a summary of, is actually just drawing the essence of what are the goals of quantum networking. So on the one hand, it is all about communicating quantum information, shuttling quantum information from point A to point B. So information transfer, but this is quantum information. And what is closely related to just shuttling qubits is actually this ability to distribute entanglement. Because if you're able to distribute entanglement between two nodes in a network, then you can use the quantum teleportation protocol to actually transfer information. Or for that matter, you can use the quantum teleportation protocol to also apply gates non-locally between two qubits at different nodes. So that's the main goal. But then when you are actually operating an infrastructure, you want to be able to deliver to certain quality of service requirements. So a quantum network should be able to, so I want to specify some metrics here. So you want to be able to demand and cater to a certain fidelity of your communication links, the rate at which you are able to shuttle information, and also from the time you place, the latency, basically from the time it takes from when you place a demand to when you actually have the demand satisfied. And also jitter, which is like, usually we know that with quantum processing, quantum computing, you never run a circuit just one time. You have to run it many, many times to build statistics. So if you're going to rely on a distributed platform for quantum information processing, and if you have to repeat something many, many times, you imagine that you want to have the same kind of the same kind of service provided by the network for multiple shots. And this has to happen within a reasonable time scale, So the metric that I refer to as jitter here is basically, it basically is taking into account the inter-arrival times, or arrival meaning here, the promise being satisfied, the cater to the inter-arrival times, and what is their distribution, so you want to have low jitter, low variance of inter-arrival times. And so these are all some very intuitive and essential requirements for a quantum network. But then towards the main goal, which is communicating quantum information, there is one primary challenge in quantum networking, and that is the challenge of loss. So whenever you're talking whenever you're talking communications, be it classical or quantum, we know that light is perhaps hands down the best carrier. So we are in quantum networking as well, largely relying on photonic communications, and photons do get lost in transmission. Not just in transmission, but also at the detectors, at anywhere you couple photons from one medium to another, you see loss. So photon loss is a huge issue, which has been very well studied in quantum information theory and communication theory. So fundamentally, we know that if you have a lossy medium or a lossy channel, the rate at which you can communicate quantum information is given by this capacity formula here. And for standard optical fiber, that is what the networking infrastructure typically is made of. This transmissivity drops exponentially with the distance. And now when you put that into this capacity formula, you really notice that the capacity for, quantum information transfer is like also dropping exponentially. So this is a huge problem in quantum networking, especially in the long distance case. And but people have solved this problem already 20 years ago, 25 years ago, and that is the idea of quantum repeaters, which I'm going to talk about briefly. But before that, the other challenge in quantum networking as of today is, at least in the near term, is that in a quantum network, resources at all the nodes are going to be very scarce. We are going to have finite number of memory qubits, and also these qubits are going to decohere. So how do you optimally utilize resources at quantum nodes is an important challenge. So that brings me to the main part of my talk, which is that so quantum networking heavily relies on these devices, these nodes, helper nodes that are referred to as quantum repeaters. And the idea is that, whenever if you want to traverse a large distance physically, you intersperse these intermediary nodes, which are actually which I'm referring to as quantum repeaters here. Now, what are they? How are they quantum? Well, first of all, they are not just classical optical amplifiers, because it turns out that just classical optical amplifiers won't be able to preserve and resuscitate quantum information as it gets lost along the transmission line. It turns out you need special purpose quantum processors, which are which contain their own quantum memories and sources and logic gates, along with optical interfaces, and only then you can actually resuscitate quantum information from point A to point B as it goes through a lossy channel. And I showed the exponential drop in the rate. Now, with quantum repeaters, what you actually end up doing is alleviating the exponent in the exponential drop. You basically make it a gentler drop along the distance. So in principle, if you place many repeaters, you can make it distance independent, at least but that's not exactly true, because all the nodes will also actually incur operational errors because they will be inherently noisy as well. But here I'm only discussing about the issue of photon loss, and so this is how with repeaters you can alleviate photon loss. But then once you have a network of, so this is like a network of repeaters now. Once you have these repeaters, how do you actually communicate? How do you achieve the task of moving quantum information from point A to point B? Well, there are a couple of different architectures, and here is an interesting departure from how you would do communication. How would we communicate in the classical world? So actually, the first architecture is similar to the classical world, and which is basically, if you wanted to move data from point A to point B, you would basically perform an encoding of that data into an error correcting code and send it on to the next hop, try to detect any errors that happen, correct for them, re-encode and retransmit. So this is like how we do in the classical world, move data from point A to point B. That exact same thing could be mimicked in the quantum world using quantum error correcting codes, and then you do some feed forward of basically encode, decode, re-encode, and retransmit, and so on. But then the departure that I was talking about is this idea of entanglement distribution networks, which Chris would like to call as actually quantum. So many people do refer to quantum networking as just entanglement distribution networks. So the idea is that all you care about in a quantum network now is to distribute entanglement between pairs of nodes, or for that matter, subsets of nodes, collections of nodes. And when these nodes have entanglement, then they can actually perform something called quantum teleportation. Which many of us here are familiar with, to basically noiselessly move quantum information from point A from between the nodes that share that entanglement. So, in fact, the whole idea of networking based on entanglement distribution is that you only ever have to care about distributing entanglement between nearest neighbors along the chain. And then you are able to teleport information even of the chain across the chain to increase the range of entanglement. So you can imagine having elementary entanglement links between every pair of nodes here. And then those entanglements are teleported through each other. And you end up with entanglement between the end nodes. And then finally, the end nodes could use that entanglement to move a qubit from one node to the other. And so entanglement distribution is this is a new paradigm for networking. So what I'm showing here is actually just a linear chain of repeaters that are doing this entanglement distribution based network. But you can easily imagine a large network with an arbitrary topology of such nodes, and think of a large a random topology. And in fact, I could show a picture like that. Yeah, right here. So imagine this is the geographical map of the United States, the west coast to the east coast, and you can have different nodes, and then these repeater nodes in the middle. And so you can imagine there is interesting questions of routing entanglement distribution between any two end nodes, any two green nodes here. Okay, so now towards that, so the problem of communicating quantum information between end nodes is now broken up into actually distributing entanglement between those end nodes. Now imagine that you're running this network, and you can cater to you're actually tasked to cater to different possible end nodes simultaneously asking for end-to-end entanglement. So you need a quantum network infrastructure that can cater to all these demands simultaneously. So you need a proper network stack that can basically look at that. One way to divide and conquer this task of moving quantum information between different pairs of nodes all simultaneously using a common resource is if you operate such a network stack where you're dividing the role of the network into different layers. And at the physical layer, for every pair of adjacent nodes here is only distributing entanglement within themselves. But then there is a higher layer, which the link layer that is sitting next up is trying to connect two adjacent links to form a larger link. Okay, and then you have the network layer whose job is to find routes between end nodes and connect them. And then there is the transport layer, which is actually going to do the qubit teleportation. And then right at the top sits an application which may be running over the end nodes. So you can imagine a sensor network that is, let's say you have different sensors at some on the west coast and east coast, and then they are using a quantum network to talk to each other and do some joint process, just joint sensing. So that's the idea of, we need such a full quantum network stack to utilize a quantum infrastructure. And what adds to, one of the challenges I did mention that adds to the complexity is that in the near term, these nodes in the helper network are going to be finite in their resources. So there is, again, another interesting associated problem of how do you not just route information, but how do you schedule operations in the network to achieve those routes concurrently for all the different flows of entanglement, flows of quantum information that are being demanded and being catered to. So there is this, there are a couple of, there is both routing questions and as well as scheduling questions here. Okay, so likewise, so I ended up, talking a lot about the long distance entanglement network stack, but here is an example of quantum network stack entanglement distribution based for the small scale short range quantum networks for quantum computing. So you can imagine now this is these end nodes are QPUs, quantum processing units in a quantum computer, and you have some centralized node whose job is to provide all-to-all connectivity between the different compute nodes. And you can imagine similar entanglement distribution between every end node and the central node. So the central node serves as a switch, and it will have restricted resources. And how do you utilize it efficiently to provide entanglement between any pair of QPUs? And the reason you need those entanglements is that they may be the end nodes may be jointly computing a circuit that requires entangling gates between qubit 1 in node A and qubit 10 in node 3, so node C, and so these kind of scenarios. And not only that, we spoke a little bit about, we also spoke about error correction. So to realize quantum error correcting codes, large quantum error correcting codes that can correct for many errors, and that also encode large number of logical qubits, you would definitely have your logical information, very likely have your logical information actually being present over multiple nodes. And so you need constant, you need logical connectivity between all those nodes to be able to perform these gates, fault-tolerant gates. And so such a network infrastructure is key. And so here is an example of a stack for the distributed quantum computing over a bootstrapped modular architecture for a quantum computer. So I'm touching 45. How much time do I have? About 5 minutes. Yes. So that was the I tried to give like a big picture for all the different questions and challenges in quantum networking. So here is now some work that we did in our group on optimizing these protocols for quantum networks at the link layer. Okay, so this is if you had trapped ion nodes and you had a long distance. It's actually distance independent. If you had a trapped ion network, and you can operate these quantum these quantum repeaters to achieve large end-to-end entanglement rates. And so this was particularly for large distances. So we were able to achieve entanglements of the order of tens of kilo E-bits per second rate across distances, end-to-end distances of several hundred kilometers. When I say achieve, these are theoretical. These are simulations and projections. We didn't do an experiment, but it turns out with trapped ion qubits, they have long lifetime, long coherence time. So you can store quantum information longer and utilize it for quantum networking better than many other qubits. And it turns out that we can achieve kilo E-bits per second communication rates. And yeah, so I didn't have a chance to talk about entanglement, the different operations that other than entanglement distribution at the link level. There is also possibility of other operations like entanglement distillation, which is when your entanglement drops in quality across a link, you can actually take several copies of low quality entanglement and get a higher quality and distill out higher quality entanglements. And this can be used in networking. And it's in fact a very important operation in networking where you try to, make sure links that are dying out, you try to, extract something out of them. And so we considered entanglement distillation protocols based on error correcting codes for trapped ion networks, and We used distillation protocols based on these so-called quantum LDPC codes. That is a very popular topic right now in error correction, quantum error correction. And we can boost the rates at larger distances for fewer repeaters. And yeah, we also have been looking at all optical repeaters. So typically all these nodes in the quantum network are based on matter-based qubits, but there are also ideas where you completely do away with matter-based qubits and instead use light clever fashions using these so-called graph states, which are multi-modal light, basically multiple modes of light that are in a highly entangled state, and we can actually have an all optical repeater scheme based on some these bosonic encoding of qubits called GKP qubits, and achieve high end-to-end entanglement rates. And then again, I briefly want to mention that some more computer sciencey topics that we have studied in our group are basically like when you have I mean we can what I refer to as a quantum switch is actually a generalization of the quantum repeater where it has multiple clients or multiple connections to end nodes. And the question of and one important thing is that these entanglement links are probabilistic. The success of generating entanglement links is finite. So sometimes in some time steps you have entanglement, sometimes you don't. But then what is the optimal action that a switch, a node and a helper node should take at any point of time is a dynamic option. And so we can actually use Markov decision processes and other frameworks where you can deal with these random stochastic events. And the question is, how do you optimally utilize your resources in the long run to maximize the throughput, for example, of the network? And so given a certain set of actions that you can take. And so we were able to bring in this framework of Markov decision processes and model a simple task of, a simple setting of a single quantum node, helper node, which could be a repeater or a switch, and it has multiple clients, and then entanglements are born between these nodes and the switch, sporadically, randomly, and then the switch basically identifies the optimal action for any given state of the network. And if you have such a optimal policy for maximizing end-to-end entanglement rates catered by the switch, then you can imagine doing a similar thing for a larger network of switches, and that would be towards optimally utilizing quantum networks. And yeah, here we also were able to use reinforcement learning from the whole. Reinforcement learning is a powerful tool as well, which can actually help us, helped us improve our results even better. And that's it. I think I'm out of time, so I just want to say that to conclude. So I hope I gave a high-level overview of quantum networking as being an important ingredient to scale up quantum technologies and also to extend the reach of quantum technologies. That is both at the short distance range as well as in the long distance scale. And yeah, key to running quantum networks are these link layer components and protocols, namely repeaters and switches and protocols for their operations. And it is key to optimize them so that you can build the rest of the stack upwards, which is with routing and scheduling and transporting qubits. So there is still a lot of interesting avenues to explore to optimize for the especially across layers of this stack when you consider different implementations at the physical layer, and so on. And yeah, there's also possible ways we can optimize the interplay between the quantum networks and the application that it is serving. So there's a lot of interesting open questions in this area, and I hope I gave a brief overview of the field. So thank you for your attention, and I'm happy to take any questions.
Thank you very much. It was very nice talk. So questions from the audience.
Yes, please.
Go ahead.
I was just wondering, what's the difference between quantum repeater and error correction code on the code?
Yeah.
So basically, is a quantum repeater is like implementation of some kind of quantum error correction code.
So there are quantum repeater protocols that are based on quantum error correcting codes, but there are others that are not as well. Like, so I did have one picture of a repeater protocol with error correction, and that is basically, yeah, this forms a valid quantum repeater protocol where you're using quantum error correcting codes to help you cross every elementary link, basically, because these are noisy communication channels between every pair of nodes, every pair of adjacent nodes. So your error correcting code helps you detect errors that happened over the elementary link and correct for them, and then you re-encode, and then keep proceeding. So there is such a possibility for repeaters, but this is not the only one. So the main focus of my work is that you don't need error correcting codes for one-way transmission, but you can actually use just entanglement distribution, have this entanglement distribution based quantum networks. Now it's a different thing that error correcting codes do help us in this paradigm as well. And I didn't have a chance to talk in detail about it, but we can use error correcting codes to come up with distillation protocols, which will help us, convert multiple copies of noisy entanglement between every pair of adjacent nodes and translate them into fewer copies of higher quality entanglement. Is that answered?
So basically, if you don't use error correction code, then like you can use other like entanglement distillation. Like you need some other protocols to correct the errors in this noisy communication. Or like at least like complement these.
Yeah, so it is actually distillation. Entanglement distillation is precisely doing the role of error correction in the traditional one-way hop on, hop off, hop communication. In the entanglement distribution picture, it is distillation precisely does what you would refer to as error correction. Yeah.
Is it, just to follow up on that, is it the same resources required, of the number of qubits, or?
It is pretty much the same, yes. There can be small differences in the resource requirements. Yeah, we noticed that, if you, compare the two following scenarios. So you could take, in the entanglement distribution based picture, you could have an entanglement between a physical qubit that you store at one node and a logical qubit that you use to create the bridge, the link level entanglement. It turns out that you doing this way, if you compare it against actually just having many copies of physical entanglement and projecting error correcting codes on the two sides to have logical entanglement, you would see that the costs are slightly different. So what we have noticed is that, yeah, if you actually project, with the distillation protocol, you actually you are more efficient in terms of the number of physical qubits. Yeah, it needs to be properly characterized. Yeah. Thank you.
So I was curious, you claim to be quantum networking, and then based on some of the traditional architecture. So now The reason, my question is, we call this, it's a quantum networking, but we are still practicing this traditional way of doing, instead of a quantum way of doing. Are there any such concern? The reason why I'm asking the question is, in my software development project management, we claim to be agile. In fact, in that agile, we're still practicing this waterfall pattern. Calling ourselves as agile. So in this case, calling ourselves quantum, but you're still doing the traditional. Are there such concerns?
I thought I had convinced you that no, there are questions that set quantum networking apart in the sense that this whole paradigm of entanglement distribution based connectivity is, I think, new, right? We don't encounter this in the classical world, like because here the resource is somehow symmetric. There is no sender receiver at the, as far as the network infrastructure is concerned, there is no sender receiver. It's just a pair of communicating parties. Now, when you connected two parties by entanglement, they could, either of them could use it in either direction actually. So it's different. And not only that, but even the way the connectivity is established by stitching together entanglements is novel, right? It's new, right? So it's not exactly just what is being done in the classical world. Perhaps you could argue that for this architecture. So if I just if all I did was just error correction, encoding, and transmit, like imagine quantum data packets. I encode, take quantum data, encode it, hop on, hop off, and so on. That you could say is just classically inspired. That's a very hard problem to do it actually, because people have tried it, and I mean there is this whole in the classical world, all these protocols like TCP and so on, TCP/IP, they really depend on retransmissions. But in the quantum world, there is this no cloning theorem that you cannot make copies of your data. So you cannot store data, copy, and send. I mean, you won't be able to retransmit. So there is the need to rethink how you would do TCP for quantum. So again, these are very much areas of research now, and I mean there are such transport layer protocols that people have developed, but it's still not finalized. Like the optimal ones are not identified yet. So I would beg to differ that it is not exactly okay. Maybe the divide and conquer layering approach and for the stack is inspired from classical world, but the architecture is still different. But I do see you. I mean, you have an important point that one has to think of this, with a new lens, quantum lens. Yeah. Thank you.
Yeah. So I wanted to ask, one of the repeater, when you have this repeater in the middle, does that kind of lend itself to eavesdropper attacks where they can just sit on the repeater? Whereas in the full entanglement distribution, you don't have to worry about eavesdropper.
Okay, so that's a very good question actually. So in establishing end-to-end entanglement, no. So quantum wise, so one of the important properties of entanglement is this monogamy of entanglement, that when two parties are sharing a maximally entangled state, there could be no other party in the entire universe who could have a share of that correlation. So when it comes to distributing end-to-end entanglement, it is not so much about security in the classical sense that we imagine eavesdropping, in my point of view. So what is, on the other hand, important is that if you were doing key distribution, on the other hand, so everything that I described for the quantum network here could very well be also used for quantum key distribution. Okay, and in that case, if these intermediate nodes were not quantum memory based and storing quantum information, instead measuring, then you had to worry about if it is a trusted node or if there could be somebody eavesdropping. So that would be my answer, that in the world of quantum networking where you're trying to distribute entanglement, I think eavesdropping is not so much of a concern. And again, you're not actually dealing with any data. The network is only providing entanglement. right? And the question is, if you have high enough fidelity for that entanglement, like close to 100%, then the monogamy property of entanglement guarantees that nobody else has a copy, has any correlation to that entanglement. So that is your, guarantee against eavesdropping.
And when it comes to losses, is there any like quantum advantage when you have a loss picture? Is the loss picture better for quantum states compared to classical states?
No, in fact, no, the drop in efficiency is a classical phenomenon that, photons just get lost. And in the classical world, you could use optical amplifiers to just boost the signal. And, whereas that's not possible in the quantum world because of the no cloning theorem. So it's actually worse in the quantum case that you cannot communicate the information of a qubit. The rate at which you can communicate information encoded in a photonic qubit drops exponentially with distance. Yeah. Thank you.
Thanks for the session, and I encourage everybody to continue discussions.
Sure, yeah.
For now,
Thank you.
Kaushik, for
Thank you.